view here. Okay, can everybody can see it on the internets? Okay, great. So I had a big plan to focus primarily on probing quantum matter in circuits using Schrödinger cats. And then I realized that the audience here maybe doesn't know so much about the platforms that Dave Schuster and I explore. And so I thought what I would try to do is give a little bit broader of a flavor of the kinds of tools that we have at our disposal for making synthetic quantum matter out of light. So more broadly, you know, my interest is in optical and microwave cavities. So we're doing all kinds of stuff from transduction to cavity arrays from quantum computing. But the two main foci for today will be sort of exploring few body physics, where the particles that make up our material system are strongly interacting photons. Okay, so one of the stories I'll tell you will be about making the material out of microwave photons that can hop between superconducting qubits. So the sort of kinetic dynamics comes from the tunneling, and the interactions between the photons come from the anharmonicity of the qubits. And then the other story will be about engineering tools for topological few body physics in optical cavity QED. And there the idea is that twisted optical cavities can create synthetic magnetic fields for light. And those photons can then be made to interact with one another using Rydberg atoms sort of as a mediator. And as a fun bonus, we're going to get to Floquet modulate this system. So with no further ado, let's hop in. So taking a step back, I think a good starting point from this perspective of understanding the tools is to ask this question: how do we make individual optical photons interact with one another strongly? Okay, and so that's a rather inconvenient. Can I even move that object up to top? Is that better? Yeah, that's better. So the basic idea was introduced by Misha Lukin and Michael Fleischauer and others. The essential concept is to use atoms to mediate interactions between optical photons. And so how does this work? Well, imagine I have some atomic medium that my light is trying to pass through, artistically depicted in purple. So the idea is that when my photon gets to this medium, it slows down. Now, we're used to thinking about this in terms of some kind of an index of refraction for the slowing. Here, it's actually slowed down a lot more than that, because the idea is if our photon is one of these red photons that can be absorbed and excited one of many, many atoms up to this p state, well, that would give us an index of refraction, but we then have another laser beam that can take whatever the excited atom is up to a very long-lived Rydberg state. Okay, and so the idea is that now your photon enters the medium, gets converted into a long-lived Rydberg excitation, okay, and eventually decays and through some kind of a collective process that protects the K vector, but basically spends most of its time as a Rydberg excitation, and so can propagate through the medium very slowly. So this is what people call electromagnetically induced transparency. It's basically a linear effect from driven oscillators. The thing that's now interesting, though, is that if I send a second photon into this medium, if I'm using a high enough Rydberg state here, then this second photon will become a p-state atom that tries to become a Rydberg atom. But these Rydberg atoms have huge electronic orbitals. We go up to like n equals 110, 120, right? So these orbitals can be a micron in size. And so what that means is that if these photons are near each other, this state is shifted enough that the second photon goes fast if it's near the first photon. And so this sort of corresponds to one photon creating like a little micro bubble, little lens that the other photon can lens off of. Yes?
So can I ask, what do you mean it slows the first photon? So I have heard before of electromagnetically induced transparency. So it's transparent, but
so the idea
is it slows it down.
Well, because the photon isn't a photon most of the time. It's an excitation of the atomic medium. Whenever it's a photon, it's moving at the speed of light because light can only move at the speed of light, right? But if it's an atom in a Rydberg state, that doesn't have to move at all, right? So and in fact, what you find is that the speed of light, effectively, if you ask how long does it take that first photon to go through the medium, is more or less set by the speed of light times the fraction of the time that the excitation spent in the Rydberg state.
Can I think about this as the omega TK being such that the group velocity gets really
Yeah,
good?
yeah, for sure.
That's the same thing.
100% the same thing.
Okay.
Yeah, okay. So this is basically the idea. And then the point is, if we can do this in a cavity, we can have a limit where even if the
that mechanism that you described is completely classical.
well,
Here's
here's what I would say. It can be, except if I have a large enough optical depth from having one Rydberg atom, that atoms nearby actually can't absorb the photon, then it's a highly quantum mechanical effect. So if I were saying that the atom that was in the Rydberg state cannot absorb another photon, simple linear nonlinear optics. If one atom in a Rydberg state blockades some optical depth of 1,000 of nearby atoms from absorbing, now you can have strong interactions between individual photons. We may not get very far in this talk, but that's great. That's you know, I'm happy to do that. Okay.
I know where the theory was done.
I was done in Misha's group. No, I'm just kidding. I'm just kidding. I'm just kidding.
Year 2000 was a very good year for physics. Right? There was
Yeah.
several theories which were done here.
I remember I started as a PhD student in 2004 and saw the paper on some of this Rydberg stuff, and it's just like, this all sounds crazy. None of it's going to work. Yeah. So remember, again, the question was, how many atoms get blocked by having one Rydberg atom? And you could have some reasonable blockade, but if you can put your sample inside of a cavity so that the light goes around a whole bunch of times, you can get an enhancement in that effect. Okay, and so we do this. We have this kind of 4-mirror cavity. Again, we have an artist depiction of a magneto-optical trap. We load the atoms into a conveyor belt. This is actually more or less to scale. The atomic cloud's a little big. And then this is an actual image. So this is about the size of the cavity mode. This is our atomic cloud. We then compress it down with some laser beams so that it's thin. The reason it needs to be thin is that we need to make sure that atoms at this end of the cloud, if they're excited to a Rydberg state, can block atoms at the other end from being excited up to the Rydberg state. That's never a good sign.
I understand why you're using the atoms, then why you want to get this quantum mechanical effect by overlapping of the Rydberg.
Yeah, go ahead. This is your fault.
In the United States, wouldn't it be better as a platform to study this strongly correlated photon interaction as a solid, in which these collective modes of the solid will do exactly what you're doing?
So here's what I would say. The key is that you need one Rydberg atom to induce a large enough shift on nearby atoms that basically they no longer produce much of a phase shift. They don't slow the light down. Okay. And so the question is, how big a shift do you need for that to be the case? Okay. So the first part of the answer then ends up being, if you use Rydberg atoms in vacuum, they can have very, very narrow line widths. And when I say very narrow, we're talking like kilohertz kind of line widths. Like, what is that? Like pico electron volts or something, right? If you do it in a solid, there's some broadening in the solid, which is then unfavorable for that kind of stuff. I would say fundamentally, if you can do it in a solid, man, you've made your life a lot better. And there is a whole community of people trying to do that with these cuprous oxide Rydberg atoms, or not Rydberg excitons. And so it's my understanding is that there's one cave that produces samples that are good. And when people have tried to synthesize their own pristine ones, they perform worse than the dirty ones from the cave. But but still getting into this limit so far, I think is not, like, they're not there quite yet. But I agree, ultimately, that will be much better. So we do this in the lab. What it looks like, we put our atomic sample into this cavity, and then we just look at the transmission spectrum. So these vacuum Rabi splittings that you saw in the last talk are what you see, these two little peaks there. And then there's this really tall peak in the middle that's quite narrow. And what that one is indicating is that our photon is mostly a Rydberg atom. This is the slowness of the light. And if that's really true, then I should have a situation where if I send light in on this peak, then I'll be able to blockade my sample. So right now I have a cavity where it has one mode and the whole thing should be blockaded by one Rydberg atom. So I shouldn't be able to excite another atom if I get one photon in this cavity. And so what I should then see is that the second photon tries to come in and reflects off. Okay, and if I look at the photon statistics from this experimentally, what I see is that conditioned on detecting a photon for like 20 microseconds on either side, this cavity, which is, like 6 centimeters long, can only hold one photon. Okay, and now you say, why is this time scale so long? Well, it's the cavity lifetime multiplied by the fraction of the time that my excitation spent as a Rydberg excitation as opposed to a photon. Okay? Okay, so that's step 0. And we're doing all this stuff in cavities. I told you about single mode cavities. If I have a multi-mode cavity, which again, we heard a little bit about in the last talk, you can now say, well, a multi-mode optical cavity, I should just ask, what are the modes? Okay? And the modes, it turns out, are Hermite-Gauss in space and uniformly spaced in energy. They look just like a 2D classical harmonic oscillator. And indeed, if you put light into this cavity off center, the photon will oscillate back and forth just like a massive harmonically trapped particle, a story we all know and love, or at least we all know. The thing that's interesting, if I have a 4-mirror cavity like this, and I twist it out of the plane, what you can see is that on a round trip through the cavity, the spatial image of the light is going to get rotated. Okay, and so what that means is that these can't be eigenstates anymore, because an eigenstate comes back to itself, and this is not that times a phase, right? But some superposition of these can still be an eigenstate. And so it turns out that as I twist more and more, the eigenstates become these rings, which for those who are optics people, we know as Laguerre-Gauss modes. For those of us who are quantum Hall people, we know these as the symmetric gauge eigenstates of the lowest Landau level.
So twisting the cavity means you tilt a mirror and you raise another one.
Yes.
And you tilt it.
Yeah.
Right. Okay.
Yeah. So to be clear, sometimes people think I want these mirrors spinning in time. I want a fixed twist. Okay. And it turns out then for light going around this cavity in one direction, it experiences a Lorentz force. And when I get that twist just right, I get this Landau level situation. So the picture you should have in your mind is we tried doing exactly what you said, like tilt one mirror and then like align it's terrible.
It was my idea.
Yeah, exactly, right? Like I'm not criticizing you, it's the right idea. What works much better is 3D printing a structure and stuffing 4 mirrors into it. And again, because our atoms can interact with these relatively narrow modes, we can just do that. Now, this has the downside that you do get PLA on your super polished mirrors, which is not so great. But it works, and you get these nice ring modes, and you can tune these cavities to degeneracy and create this kind of a Landau level for light. And if you zoom in on this point, you can see that we can make these modes degenerate to a megahertz to a couple of megahertz. And so then the question that you should ask yourself is, what's the energy scale of our interactions that we can generate via our Rydbergs to mix these modes to try to make fractional quantum Hall states of light. And again, that energy scale is sort of megahertz. So you say, we more or less should be good to go. So this is what this kind of cavity actually looks like. You need electrodes to control stray electric fields. You need to be able to fine tune it to the right length. Indeed, the cavity that I showed you there had a nice big mode waist. And the last challenge is you have to tune all of these modes to degeneracy, but with a very small mode waist so that the Rydbergs can induce the interactions. And when you do that, you get these horrible looking avoided crossings between the modes coming from aberrated optics. So the question you should ask is, if we kind of have a lambda, so to be clear, this is not data, except insofar as Mathematica is data. But if you want to look at this paper, we do have the actual data in there. So the question is, if we can't quite tune the modes to degeneracy, is there still a way that we can make them act like they're at the same energy? Imagine they're uniformly spaced, and you want to make them act like they're at the same energy. So what should you do? Well, obviously, you should shake the heck out of the system at the energy difference between the modes, okay? And so the last piece of this story, which I think is quite fun, is we need to couple our cavity mode to the p state of our atoms, right? And that's going to give us some avoided crossing between the atoms and the light, and then this photon gets absorbed by the atom, can then be excited up to a Rydberg state. The challenge is, we just said, well, the next mode of the cavity is at a different energy. So what should we do? We should shake the p state back and forth at a frequency given by the energy difference between the modes, right? And that'll put sidebands on the state. Now, it won't make more states, but it will mean that this state then lives at multiple frequencies, okay? So the way we do that is by choosing a laser that can go from the p state to a d state and driving it, or excuse me, choosing a D state and then driving with two different tones here that constructively and destructively interfere to shake this state back and forth at these kind of tens to hundreds of megahertz kinds of frequencies. And when you do that, you should get these sidebands on the modes. And indeed, we do this, and it works quite nicely. So if you don't modulate, these are the kinds of avoided crossings that we looked at in the last talk. If you do modulate, here at like 50 megahertz, you get smaller avoided crossings that follow Bessel functions at the multiples of the modulation frequency, and the more strongly you modulate, the more copies you get. Okay? And then if we also add this beam that goes up to the Rydberg state, you can see your EIT feature, this Rydberg excitation feature, repeated at each of these places. So I want to be clear, this is sort of a weird thing. What it says is, I drive at any of these energies, okay, and I excite up to the same Rydberg state. I still only have one blue laser, one 480 nanometer laser, because there's only one state here. It can just be accessed at multiple frequencies. And this is how I think you should think about these kind of Floquet copies that, like, we see something pretty similar, right? It's not making multiple states here. It's copies or multiple addresses where you can reach the same state. So what I probably don't have time to explain in detail is how we put all of these ingredients together. I think maybe this says that it's time for me to get a new one of these connectors, but I don't think Amazon can deliver fast enough. So I think we'll have to make do for the rest of this talk. How we make Laughlin states in this system. This is the reference. The basic idea is to inject photons that we generate with a DMD to have orbital angular momentum into this cavity. And what you discover is that these photons can then collide and become entangled with one another in a way that they're sort of orbiting each other due to this Landau level configuration. And then we can measure the angular momenta of the photons coming out using mode sorters and look at correlations between their angular momentum. Okay? So, I guess this isn't normally how it's done, but maybe I should say, are there any questions on the first half before I go on to the second half? Yeah.
In principle, I'm not saying, could you move the cavity mirrors and do the same instead of modulating the, yeah.
Great question. Moving the mirror at 10 megahertz would be hard.
Yeah.
Okay.
Fine, put an acousto-optic modulator.
Exactly. So
Yeah.
you could put an EOM in there
Right.
and get the same effect. And we've started to think along these lines. You know, if you look on my group website, we've got all kinds of stuff where we use atoms to stir light and atoms to modulate and all this stuff. But the problem is you work super hard to get atoms, And my sense is you should use your atoms for their nonlinearity because they induce loss, right? For everything else, there's MasterCard, right? By which I mean, like, you should put lithium niobate in your cavity. And so we're partnering more and more with people like Amir Safavi-Naini, and by people like, I mean with Amir Safavi-Naini, to be able to have these kind of active control capabilities coming literally from nonlinear optical materials that are less lossy. Okay?
How many photons do your chocolate stage have?
2. So Monica, in her talk, was selling that Marcus has made 2 atom Laughlin states. We have made 2 photon Laughlin states. And one of the real challenges here is that you should really ask yourself, how far could we scale this, right? If you want to see anyons, my take is you need something like 10 particles. And the interesting thing is that in this regime where the Rydbergs mediate interactions between our photons, the figure of merit is the collective cooperativity of your polaridon, okay? And the collective cooperativity here, only because we have these Rydbergs to mediate the interaction, right? Can we use the collective one? Otherwise, it would be the single particle cooperativity. But the key is that the number of collisions you can get between your particles before the collisions tear the quasi-particles apart is the square root of the cooperativity, right? And so what that means is now you should ask yourself, if I want to make a 10-particle Laughlin state, how many collisions in total do I need to assemble that, to entangle the particles enough to build that state, right? And what cooperativity does that imply is going to be required for my science? Okay, so we can get, we think cooperativities we've seen as high as like 5 or 10,000. But here's the thing that's interesting, and this is a perfect lead into the second half of the talk. The superconducting qubits that I'm going to tell you about now have an effective cooperativity of about 100 billion. Okay, and so that's why I would say, if what you really want to do is build strongly entangled states of photons, you get amazing capabilities with the optical photons for Hamiltonian engineering, right? But if what you care about is building the biggest, most entangled state, you should use the microwaves.
May I ask maybe probably the question is silly, but these 2 photons which are in the Laughlin state, do you have any idea what kind of statistics or correlations they're actually obeying? Do they fall in any of the known categories, or is it something completely?
So it's a 2-photon bosonic Laughlin state at half billion. So
This I understand from like characterizing it as an analog of, but their sort of correlations, are they sub-Poissonian, screw-Poissonian,
So-
they fall in such category or not at all?
So what ends up happening, they're not in one mode. So the normal stories that we tell, and that's some of what actually makes it interesting. The normal stories we tell about sub and super Poissonian are about correlations in time in one mode. So that's why I said we have a mode sorter, right? To sort them into angular momentum modes. And then we can make correlations between time and angular momentum. We can also make correlations between position and time. And so we see they avoid each other in space.
So you have space-time correlations.
Yeah. Right. So one of the challenges to me going forward is going to be to integrate this with like high-speed camera technologies to be able to get that information out fast. But again, much of the information we got out was correlations in angular momentum, and a camera doesn't give you that, right? Like some kind of mode sorter gives you that information. Take a look at the manuscript. It's fun. Well, it was fun for me, but I wasn't in the lab, so. Okay, good. Okay, so in the second hour, I'm going to tell you a little bit about microwave photons. Did you want to take a break before we do that? Okay. So
Maybe I'll ask this question.
Uh-huh.
You've shown their logos twice. There's this large publishing house.
Yeah, we took their logo. Yeah.
I know.
Mhm.
Have you and David thought about publishing them?
Yeah, so actually, this is a great question. So, I collaborate very closely with Dave Schuster and his group. The circuit QED experiments I'm going to talk about now live in his space in his dilution refrigerators. Dave is amazing. He's a great scientist. And when we started working together, we decided we needed a logo. You know, half of our groups are sort of shared between the two labs. And we thought the best thing to do would be to take the publishing house's logo. And our hope is that someday someone cares enough about what we do that they find out and sue us. But I have to be honest, I think we're pretty far from that. Although I guess they were recently acquired. And so I got a bunch of emails from people making that. Do they have, what journals do they have? Write a book. You know what? I get lots of invitations to write. If anyone would like to write a book, I can send you some of those requests. Okay, this is incorrect. That you'll see the link later. Okay, so previously I was telling you about particles moving around in the continuum, right, in a lowest Landau level. I'd like to talk to you a little bit now about making lattice models for microwave photons. Okay, so the idea is that electrons hopping around in some ionic lattice is something we can simulate with microwave photons hopping around in some kind of circuit lattice. So the question is, what makes a good lattice site? An LC circuit makes a good lattice site, right? The frequency of the photons that can be trapped there, kind of like the rest mass, is 1/√LC, which for us is going to be about 4.5 gigahertz. So the good news is these things are easy to make. The bad news is that photons in a site like this don't interact with one another. What do I mean by that? Well, if I quantize this LC circuit, it can have 0 photons, or 1 photon, or 2 photons, or 3 photons, and the energy to add another photon is always 4.5 gigahertz. Well, I say always, but if you've ever made one of these in the lab, what you know is that if you drive your signal generator hard enough, eventually this thing will give out the magic smoke. But before it does that, it kind of heats up and deforms a little bit, right? And when it deforms, the resonance frequency shifts, okay? And that's the kind of nonlinearity that I want, right? If I get enough photons in there, the resonant frequency starts to shift. The downside is that I don't want this to happen at 10 to the 15 photons, right? And I don't want energy to leave as phonons, right? Measuring the state of the system. I would like it to happen at like 1 photon. So what that says is if I wanted to use heat, I should make this LC circuit as small as possible, right? The smallest LC circuit I can make, or Dave can make, is a transmon. Yeah.
So since you're saying that this is deformed into something anharmonic, can we think of it like an anharmonic oscillator, like a molecule or something in some sense, or
So-
it's too imaginative?
So I think a molecule would be a great option, right? A 2-level atom is also a great option, right?
But the 2-level atom doesn't have more than 2 of these.
Well, but think about a rubidium atom, right? We have
it's a
5s,
multi-
5p, 4d, or sorry, 5d, so that's 780, then 776. You have some anharmonic spectrum. The point is, we think of it as a 2-level system because the anharmonicity is so huge compared to everything else in the problem that you never couple to anything but those 2 levels. But my view is it's more or less the same here. We can talk about how this works microscopically. I'm a cold atom person. I know there are a lot of condensed matter people here. So rather than try to make an argument about how a Josephson junction works, what I'm going to say is that the inductance depends on the current. And that gives us a situation where nobody can disagree with that, right? So the first photon that goes into the system will be a 4.5 gigahertz photon, and then the second one will be 4.2 gigahertz. And so that means if I put 2 photons in this site, I have like 300 megahertz times Planck's constant of attraction between the photons. Yes. He disagrees with that treatment.
Well, this would be sort of like attractive interaction between photons.
So, yes, exactly. So you might ask, do we care about attractive versus repulsive? For the most part, if the model is non-dissipative, we actually really don't. Okay, so we get 300 megahertz of attraction. If we want to couple 2 sites together, we just put a capacitor between them. Okay, so we'll choose the capacitor to have about 10 megahertz of tunneling. Oops. And so then the question you should ask is like, what's my interaction energy and what's my tunneling energy compared to how long my photons live? Well, they live for about 40 microseconds. So that's something like 12,000 collision times or 400 tunneling events, right? Which incidentally, these numbers don't look anything like cold atoms. Those numbers look an awful lot like cold atoms. Okay,
Sorry, how can you tune this? Like, how much can you tune J?
J we can tune to whatever we want. So in practice, we would love to have had J a little bit bigger. There's no reason to have 10 megahertz compared to like 40. But it turns out the way we do readout of the system is by tuning our qubits away from each other and then looking at dispersive shifts of the cavity. And you'd like to tune them away fast compared to everything else. And going much faster than 1 over 2 pi 10 megahertz gets a little tricky. Okay. How are we doing on time here? Doing all right. So this is what the actual apparatus looks like. So here we just have capacitive couplings between 7 qubits. These are readout resonators where we can measure dispersive shifts of these qubits or the cavities that are determined by the state of the qubit. So we can see how many photons there are in each of these cavities. And then we have flux lines to drive them and adjust their frequencies to whatever we want. Okay, so one fun thing here is that our experiment, well, I realize this slide was originally made for a BEC audience, cold atoms. So you say it's super fast. Each experiment is less than 10 microseconds, where theirs are like 30 seconds. And I know you guys are condensed matter people. You're like, our system reaches equilibrium in a picosecond. What are you talking about? So anyway, this is good for us. Coming from cold atoms, I think of this as quite fast. Okay, so then there are a couple of kind of fun stories one can tell here. And you know what? I'm going to make an executive decision. I'm not going to tell you about reservoir engineering. So what I will tell you, if you want to hear about reservoir engineering, grab that link real fast. Go, 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 go. Nobody wants to see. That's what I thought. Nobody wants to hear. He wants to hear about it. Bless your heart. Okay. So what I think is kind of a fun story to tell here is, how one can make many body states of these photons, I think in a way which is kind of different than what one can do in a lot of other platforms. So what we would like to do is adiabatically prepare strongly interacting fluids of microwave photons. Okay, and so the way I want you to think about doing that is we're going to start by preparing arbitrary single particle eigenstates of this system. Okay, so how do we go about doing that? Well, I told you I can set the energies of these sites, so I'm going to have them staggered. Okay, so this will be a situation where if I put a photon in here, it can't hop anywhere because every site is at a different energy. Okay, so that means I can prepare any eigenstate I want. This is the highest energy state, that's the second highest, that's the third highest, fourth, fifth, sixth, seventh, so forth. Okay, so if I want to prepare the highest energy state, I just put a particle in there. Now, somebody asked earlier about highest versus lowest. Because U is negative, we're preparing the highest energy states. But everything's symmetric, it doesn't really matter. Okay? So now what I can do that's fun is adiabatically remove this disorder. Okay? And then my photon should delocalize over the whole lattice. And I have the lowest energy, or sorry, I guess here, highest energy particle in a box state. Just one photon delocalized over the whole system. And if instead I put my particle in the second highest energy state, then when I remove my disorder, I prepare the second highest energy state of the system. Okay, and indeed, we can actually even do this in the lab. So this is actual data versus where we stop in this disorder ramp. Okay, and indeed, if you make it all the way into to the end of the disorder ramp and measure, you get this lowest energy particle in a box state. And if we do the same experiment for this second highest energy state, we make the second highest energy particle in a box state. Yes.
You would reverse to map out for this.
Smart ass. Yes, that's where we're going. Very good question. So here's the thing that you would want to ask. How slowly do we have to ramp? And here we know the answer, right? How do we tell? Did we make the state we meant to make, right? But imagine you don't know what that state ought to look like. So what I say you should do, ramp forward at some speed and then ramp backward at the same speed. And ask, did my particle come back to the place where it started? Okay, and if it did, then either I ramped so fast that I jumped through all of the diabatic transitions and then jumped all the way back through, which is the super fast ramp limit. Or if I ramp 1,000 times slower, I'm fully adiabatic in this direction and then fully adiabatic coming back. And then I can guess that in the middle, I made the state that I wanted. And it's only for these 3 orders of magnitude in time in between that I don't come back, right? And that says I was non-adiabatic in this rank. Okay, so this is 1 particle. We can do this for 2 particles. And then when we remove the disorder, we get something that looks like this. We can do it for 3 particles, 4 particles, 5 particles, 6 particles, 7 particles. Works great. We can look at the correlations between the particles, and we see that they collapse onto some rescale Tonks-Girardot kind of a story, right? And again, you know, if you're sort of in the know here, you said, well, U is much larger than J, right? So this really should just be like a 1D Tonks gas kind of a model. We know exactly what should happen, and indeed we do, it works. I would say this is more of benchmarking the capabilities and the ideas here than exploring qualitatively new physical models. The last thing I wanted to share with you all is that we can make superpositions of many body states. So what I showed you was that we could pi pulse a particle in here, and then if we melt, we get a state like this. We can pi pulse a particle into the second lowest energy state, and then if we melt, we get this 2 particle state, and then if we pi pulse the 3rd particle in, we get this Tonks gas. What if I replace that 3rd pi pulse with a pi over 2 pulse? Well, if I look at the average evolution, I got the average of the 2 particle density and the 3 particle density. But really, the thing you should ask yourself is, have I made some statistical mixture of 2 and 3 particles, or have I made a coherent superposition of 2 and 3 particles? So let me tell this story in a slightly different way. For the last particle, I pi over 2 pulse it in, and then I evolve forward. And what I said we should do is just measure, right? And so we have the superposition of an n particle state and an n plus 1 particle state. We just measure. We saw something that looked like the average. Nobody's that excited about that. But what if I apply that pi over 2 pulse, evolve forward, make these 2 states, wait for some amount of time to accrue a phase between them, set by the many body energy difference between n particles and n plus 1 particles in the system, then adiabatically ramp backwards. And so now I should have, in that single particle, I've relocalized the phase information of those 2 many body states. And now if I do sort of a tomography or Ramsey on that single particle, I should be able to extract the phase difference between those 2 many body states. So we call this like a many body Ramsey sequence. We can do it for superposition of 0 and 1 particle versus whole time. We get these beautiful fringes. We can do it if we're non-adiabatic, then we make many frequencies, because we make many intermediate states that we can Fourier transform and see. And then you can look versus how slowly you ramp, that you have many Fourier features in this plot. So we can do it, and then for the slowest ramps, you make 1 Fourier feature, meaning you just have a superposition of 2 states. We can do it for 1 and 2 particles, 2 and 3 particles. This energy difference between n and n plus 1 particles is a direct measure of the chemical potential, right? How much energy does it cost to add 1 particle to the system? It's hard for us to otherwise measure the chemical potential directly, but indeed, we can make this measurement versus how many sites we allow in the system and how many particles we put in, and we really see that it exactly follows what you expect for this kind of a Tonks gas. It just operates beautifully. So I think in the interest of time, I will stop there, but I will just say we can make superpositions of system sizes. We can make cat states in this kind of an approach. And more broadly, I think it suggests really exciting opportunities to kind of combine baby quantum computers and ideas associated with baby quantum computers with synthetic matter to come up with new ways to learn about the material systems. So with that, let's go to the most important slide, which is the folks who actually did the science, and thank them for their hard work and you for your attention.
So could you also, instead of doing a superposition of n and n plus 1, do a superposition of n and n, but with different energy states and measure the energy spectrum
So, in fact, that one, you have to think a little bit about how you would do that. And what you end up having to do to implement that is perform conditional particle injection in the disordered configuration using interactions between adjacent qubits. So if you look in the supplement, we actually do it, right? And so you can measure those energy differences too. You could imagine going into, more than two states at the same time. Sunwon suggested that if you had your evolution time controlled by a set of qubits, for example, then you could do a quantum Fourier transform and do phase estimation in a single shot to extract the frequency evolution directly. So I think there are all kinds of fun ideas along exactly those lines once you start allowing yourself gates.
It's always great to hear this stuff, but I'm really curious. You guys thought about ways to expand this kind of like more intractable systems, like either higher effective dimensions or more size, but what are difficult?
So the real difficulty with the transmons is control. Okay, so we have to be able to control the individually the flux going to each qubit. It's kind of a pain, and so what I think our next set of experiments is going to look like is a slightly disordered system that we don't have full control over with like 50 or 100 qubits, and then the idea will be to adiabatically inject particles via one or two sites that you do have control over. I pulse a particle in, adiabatically turn it through your system, and so forth, and combine that with these sort of conditional ideas to probe it. Because previously, without these kind of Ramsey probes, it wasn't clear what you would look at with that kind of a tool. So I think it's a kind of fun hybrid of, a solid state system where you're doing transport, but you can have a big system, right? In our systems where you have control of everything. So anyway, yeah.
So let's thank Jon.